A student stands a distance L from a wall and claps her hands. Immediately on hearing the reflection from the wall, she claps her hands again. She continues to do this so that successive claps and the sound of reflected claps coincide. The frequency at which she claps her hands is F. What is the speed of sound in air? Okay, so speed of sound, distance equals speed times time. Therefore, speed equals distance over time. Okay, so what we know is that the frequency is linked to the time it takes for the sound to go there and back. So every time the sound travels a distance 2L, she claps her hands. So it does it in time t. Okay, so the speed is distance divided by the time it takes to travel that distance. And we know that t isn't one of the possible answers. We need it in terms of f. So how do we convert from t to f? Well, f is 1 over t. So we can say 2L times 1 over t equals 2LF. So the answer is D. Question 22 is about a standing wave, and this time it's in the second harmonic and it's open at both ends. So we're going to get antinodes at both ends of the pipe. Okay, what is the phase difference between the motion of a particle at P and Q? So what we need to know is, are they in the same section of the standing wave, if you like? Are they within the same node section of the pipe? If they are, then the phase difference is 0. If they're not, then the phase difference is pi. So we need to draw the second harmonic. So I know I have an antinode here and an antinode here. Now the first harmonic looks like this. That's the first harmonic. We want the second harmonic. The second harmonic has 2 nodes inside the pipe. So it has a node roughly here and here. Okay, so I can use that to guide me. So this isn't going to be beautiful, but it's going to look something like this. Something like that. All right, I can make that a bit cleaner. Okay. Always looks better in your head than when you draw it. Okay, so now I can quite clearly see that P is in one section and Q is in the next section, the adjacent section. So it's pi radians. And the reason for that was in, let me find it, question 16. So if you look at the previous video, question 16, I explained why in a little more detail. Okay. The motion of an object is described by the equation A is proportional to minus x. Okay. What is the direction of acceleration relative to displacement? And what is the displacement when the speed is maximum? Right. Direction of acceleration relative to displacement. It's all about this symbol here. What that means is we're kind of looking at vectors, we're looking at directions here. So if the displacement was downwards, the acceleration is upwards, and vice versa. If displacement is from right to center, the acceleration is from center to the right. So it's always opposite. This negative symbol means opposite. So it's going to be C or D. Now, when the speed is a maximum, so to understand this, we need to draw perhaps a little pendulum. It's going through here. Okay, it's going back and forth. So here it has 0 speed because it's reached the maximum and then it's about to drop back, and then it slows down, reaches the maximum, and then drops back. Here in the center, as it passes that equilibrium, it's always the maximum speed. And it doesn't matter whether it's a spring that's going up and down. In the center, as it passes through the center, that's where you have the maximum speed. So it's got maximum speed here when it's closest to the equilibrium. In other words, the displacement, the distance from the equilibrium, is 0. So it's going to be D. 24. A particle moving in a circle completes 5 revolutions in 3 seconds. What is its frequency? Okay, so frequency is the number of waves, cycles, circles per second. Okay, so you could say it's the number of revolutions in 1 second. All right, so it completes 5 revolutions in 3 seconds. So it's 5 per 3 seconds. So it's 5 divided by 3, hertz, which is the unit for frequency. And 25 is about traveling waves, moving through time, moving with a medium, in a medium. They're out of phase. They're not on top of each other. We can see that they're not quite in phase. They're out of phase, and they're actually 90 degrees out of phase. In other words, you can see, how can I describe this? Let's have a look. The easiest way to describe this is probably by showing you the difference compared to a full wavelength that they're out. Right, so if we take a full wavelength, we can see that the first wave, the blue one, ends at 5 seconds. So the period is 5 seconds. Okay, so milliseconds. Sorry, I've just looked at the units here. Milliseconds, not that that matters, but the period is 5. However, the second wave starts like 1.2-ish. Later. Okay, so it's behind, one of them's behind by 1.2 milliseconds. In other words, 1.2 divided by 5, which is about a quarter. Okay, so it's about a quarter of a wave out of phase. If it's a quarter of a wave out of phase, that's a quarter of 360 degrees, or 2 pi radians. Quarter of 360 is 90. So the phase difference between them is 90. The resultant displacement, you have to add up the two. So at t is 2 milliseconds, we're here and here. So we have a +1 plus a minus, I'm just going to rub out this blue line so I can see it, plus a minus, I'm not sure what that is, 1.6, minus 1.6, I'm not sure. Okay, plus and minus 1.6, so the answer is negative 0.6. D is going to be the final answer.